For decades, titanium has been called the metal of the future. But if it's such a remarkable material, why hasn't it replaced steel or aluminum after more than 2 centuries since its discovery? In this video, we'll uncover why titanium remains one of the world's most impressive metals and why its future may still lie ahead. Titanium was discovered in 1791 by the British chemist William Gregor, who identified its oxide in the mineral ilmenite. However, extracting pure titanium proved to be an enormous technological challenge. The first sample of pure titanium was produced only in 1910, while industrial-scale production did not begin until the 1940s. The problem was that producing it was incredibly difficult, energy-intensive, and prohibitively expensive. As a result, for decades, titanium remained largely a material for laboratory research rather than industrial applications. Even so, researchers found several practical applications. Titanium dioxide turned out to be an outstanding white pigment. Because it is non-toxic, it is widely used in products ranging from food and cosmetics to paints and pharmaceuticals. During World War II, titanium tetrachloride was also used to generate smoke screens. The real breakthrough, however, came during the Cold War. The arms race forced both the United States and the Soviet Union to search for materials with better performance than conventional steel and aluminum. Titanium quickly attracted attention because it offered a unique combination of properties. Its greatest advantage is its exceptional strength-to-weight ratio. In simple terms, a titanium component can provide the same strength as a steel one while weighing significantly less. This makes titanium ideal wherever reducing weight is critical. For example, in aircraft where every extra kilogram increases fuel consumption. Titanium offers several other important advantages as well. It is highly resistant to corrosion, non-magnetic, and capable of maintaining its mechanical strength at elevated temperatures thanks to its relatively high melting point. These remarkable characteristics made possible some of the most ambitious engineering projects of the Cold War. One of the best-known examples is the American SR-71 Blackbird reconnaissance aircraft. The need for such an aircraft arose because intelligence gathering had become increasingly difficult. Although satellites had already reached Earth's orbit, early space reconnaissance suffered from limited image quality due to the high altitude of observation. A logical alternative was a reconnaissance aircraft capable of flying much lower while remaining beyond the reach of enemy air defenses. Initially, modified bombers were used for this purpose, but they proved vulnerable to Soviet fighters and anti-aircraft artillery. The next step was the U-2, which could fly at altitudes of around 21 kilometers, high enough to evade both Soviet fighters and anti-aircraft guns. That advantage did not last long. The Soviet Union developed surface-to-air missile systems capable of engaging targets at much higher altitudes, making the U-2 increasingly vulnerable. As a result, engineers were tasked with creating an aircraft capable of flying even higher and at speeds exceeding Mach 3, fast enough to outrun incoming missiles. This requirement led to the birth of the Blackbird. Designing such an aircraft presented enormous engineering challenges. At speeds exceeding 3 times the speed of sound, friction with the atmosphere generated tremendous heat. Even at an altitude of around 27 kilometers, where the air is extremely thin and cold, the aircraft's skin could reach high temperatures. Under such conditions, aluminum lost much of its strength, while steel was simply too heavy. Titanium was the only material that combined the necessary heat resistance with low weight. But there was another problem. At that time, no country had ever built an aircraft using titanium on such a scale. The United States didn't even have sufficient domestic production of aerospace-grade titanium. Ironically, much of the titanium used to build the SR-71 ultimately came from the Soviet Union itself. Through a network of shell companies, the CIA secretly acquired Soviet titanium, which was then used to manufacture one of America's most advanced reconnaissance aircraft. In 1964, the Blackbird entered service. It became the fastest, highest-flying operational aircraft ever built. Soviet missiles simply could not catch it. Despite its extraordinary performance, however, the SR-71 was never produced in large numbers. Manufacturing and operating the aircraft were extremely expensive, maintenance was exceptionally demanding, and titanium itself remained scarce and costly. The Soviet Union also sought to exploit titanium's unique properties. One of its most ambitious projects was the K-162 nuclear submarine. Soviet engineers wanted a submarine capable of traveling at unprecedented speeds while remaining difficult to detect. After evaluating various materials, they concluded that titanium was the only practical choice for the pressure hull. Although the USSR possessed its own titanium industry, production costs were enormous. The submarine became so expensive that it earned the nickname the Golden Fish. Several additional titanium submarine projects followed, but they too were eventually abandoned because their cost was simply unsustainable. Today, decades later, manufacturing technology has improved dramatically in many fields. Yet one problem remains largely unsolved. Producing titanium is still expensive. As a result, titanium continues to be a premium material. Global production of titanium sponge amounts to only about 300,000 tons per year. For comparison, annual aluminum production exceeds 70 million tons, more than 200 times greater. This is especially remarkable because titanium itself is one of the most abundant elements in Earth's crust. Demand for titanium has been steadily increasing, but its use remains concentrated in industries where material cost represents only a small fraction of the final product's price. A good example is Apple's iPhones with titanium frames. Although titanium is more expensive than aluminum, the additional manufacturing cost is relatively small compared with the overall price of the phone. Titanium is also widely used in aerospace, where even small improvements in weight, strength, or heat resistance can justify significantly higher production costs. For most industries, however, cost remains the deciding factor. As long as steel and aluminum can deliver acceptable performance at a fraction of the price, they will continue to dominate mass production. And that is why, despite its extraordinary properties, titanium has never achieved the widespread adoption many predicted 70 years ago.